Thanks a lot, Francesco, for the kind introduction. It's a really pleasure and an honor to be here and to join the seminar. And I'm building a little bit on the previous lecture given by Björn Christensen, which you already mentioned. So it was really nice that he gave you already the background for the light scattering. And I will talk today about lignin. Right. So why do we need molar mass of lignin? There are a lot of different reasons, but at the end, we all want to apply lignin in a larger scale, which we are hopefully getting there in the near future, but we are still have some troubles. And what we basically need is a structure property application relationship. And of course, a lot of functional groups and a lot of different characteristics of lignin play a role here, but also molar mass is kind of important of a parameter. When we try to understand lignin, we have to consider a lot of different aspects. It's not just the molar mass, it's also the shape of the molecule, compactness, which of course is influenced by molar mass, but which simply influenced by the structure in solution. We have to talk about dispersity. I will come back to that a little bit later. Of course, there is a chemical structure and there is a very large heterogeneity, which is a little bit bigger, I would say, as if we talk about cellulose, for instance. So all this comes together at a certain point and we have to address. Now, don't worry, I don't want to tell you what lignin is in terms of building blocks. I just want to give you a little bit in historic perspective how we see the structure of lignin now, how people saw it before, because this is also to some extent related to how large is the lignin molecule. And the first structure in literature we could find was the one from Joseph Martin from Charleston Research Lab. It's from 1964. Just remember, this is about 12 years after Staudinger got the Nobel Prize for the concept of polymers. So the concept of big molecules at that time was pretty new. I think that was not so much addressed here, but we see already the first structural elements of lignin. Some are correct, some are maybe not. And then, of course, there's Carl Freudenberg, who came up with a lot of lignin research and also with a lot of models. And what you see is already this concept, lignin is a big molecule. At that time, people thought that lignin is much bigger than we know it is today, although we don't know the lignin molar mass in a tree. But researchers, after the concept of a macromolecule came up, thought that the lignin molecule in a tree is so large that you can poke in a tree and a trunk somewhere down and then somewhere far up and you will hit the same molecule of lignin. Of course, that we know today is not true, but it's just like the strength of a tree is so impressive that they thought it's going to be, has to be a very, very strong, large molecule to sustain basically the tree against gravity. And then in the 70s, we have the model from Glasser and Glasser. And you see here already that it's big. It's a big molecule. And of course, you have to keep in mind, these are all models. Just a Swedish model here from Erich Adler, also from 70s for the spruce wood. And then we had a little bit a game changer here, which was Gösta Bruno in the 90s, because he found a couple of new structural elements by the application of NMR. And then, of course, we have the native lignin structural models from John Ralph. What is different here is basically that these are for the first time, what you see here, the structural elements, they are all confirmed in connectivity by NMR. So that piece is not just a model, this is real. It doesn't show us how the whole lignin is, but it gives us quite a good idea. And then we have for the first time the interplay of molar mass and functional group. So what Misha Balakshin from Aalto University did, he used our absolute measurements of molar mass, in that case for milkwood lignins, so to have a real idea on how big the molecule is, and then try to fit that with all the structural elements which had been analyzed by other methods. So this is a model still, but it's a quantitative model also towards the size of the whole molecule. So this is basically what we have now. So as I said before, we don't know how large the molecule of lignin in a tree is. We don't know how large a molecule of cellulose in a tree is, or in wood is, because basically we destroy the polymer to some extent when we try to isolate. And we can try to do that in a moderate way, but usually we do some harm to the polymer as such. Then we can say, okay, come on, it's a very academic question. Do we really need to know that? To know that? Yeah, sometimes for curiosity-driven research, it would be interesting to know, and maybe we are getting there sometimes in the future. Currently, we have no answer to that. So we need an idea to dissolve lignin without any degradation, and then lignin would dissolve wood without any degradation. So ionic liquids don't really help us here, but maybe we get there in the future. And then we have the molar mass of isolated lignins. We have Kraft lignins, we have lignosulfonates. We can also say, okay, as long as we can compare them, I don't care about the real numbers, but it would help us, because it would help us in interlaboratory comparisons, for instance. So if one lab measures lignin, it's usually, even though it's the same lignin, it has different parameters. And if you have an absolute method here, it still will not be perfect because it's a different lab with slightly different conditions, but we would get much closer to a more comparable number. So for that reason, it makes a lot of sense to go after the real molar mass of also technical lignin. So this is part of the motivation. Now, sometimes the answer is simple. This is just taken from a paper I reviewed a couple of years ago. It was put very simple, lignin. There is a nice formula given, and we have here the molecular weight with 3-digit after the comma, so quite nice. Of course, it's not correct, but it felt really nice to say, okay, that's it, that's what it is. So let's see whether this 1,513.599 grams per mole are correct or not. We will see. What I also want you to a little bit have in mind is that lignin is a very generic name for a lot of different things. So there's Kraft lignins, and there's different Kraft lignins, not just because they are softwood and hardwood and mixtures. So different processes, different parameter in the same process. So there are a lot of different lignins out there, and there is lignosulfonate, and there's a lot of different lignosulfonates, and there are biorefinery lignins. So it's always important that we really specify. And also for analysis, it's a huge difference if we analyze a lignosulfonate or if we analyze a Kraft lignin, and I'll show you some examples afterwards. So just keep in mind, make sure you choose your method really according to your lignin needs once you have to choose one. And the second point, before we can even start to analyze our lignin, is purification isolation. That is also a very important step, and it has a large influence on your final result, no matter if you have an absolute method or not. So it's a bottleneck in terms of lab work. So if you get a black liquor, it doesn't mean you got lignin. You got the black liquor, you have to isolate the lignin. You have to separate the process chemicals. You have to separate the sugar molecules, the degradation products, because all this could influence your lignin. And just make sure you do the right job here, or at least when you get a lignin and analyze it, you just ask for how has it been treated, because that has a big influence as well. Now, I saw that Björn Christensen talked about dispersity, because that is really very important. All polymers are dispersed. So the old name, polydispersity, although we shouldn't use it anymore according to UBAC, basically gives us the same. We have differences in polymer chain length. So for cellulose, it's easy. We can always compare it to a pack of spaghetti. Same length of the spaghetti when we buy them means a very, very high uniformity. This we usually only have with proteins, but classical polysaccharides and also lignin, they have very different chain lengths. So you hop on that spaghetti pack and you get into the situation of cellulose, of alginates, and also of lignin. So different lengths of chains. But for lignin, it's a little bit more complicated because lignin is a branched molecule. So we have different branching parts in there. The composition is different, and the composition is not uniform across the whole molar mass distribution. The end groups are not always the same. The charge might not always be the same in a lignosulfonate. So we have a very, very high degree of complexity, and this also affects the outcome of all molar mass distribution. So just keep that in mind when you look into lignin and molar mass distribution. So there are a lot of different methods in the literature, in different labs, how to measure the molar mass distribution of lignin. Of course, first you have a size exclusion chromatography, so you separate the different molecules according to the hydrodynamic volume, usually on a swollen polymeric gel. Björn Christensen put it quite nicely. You have this cauliflower type of little gel molecules which interact basically with your polymeric molecule, in that case lignin, and you should only have an enthalpic interaction and entropic interaction and no enthalpic interaction. So you do that separation, and for that you need a certain solvent. And of course, it's always nice if you have one unique solvent which fits all your lignins. Sodium hydroxide, water and salt, that might be something where you could directly dissolve most of the lignins. It also works for lignosulfonates. And you don't need to do anything with your lignin in order to bring it into solution. But there, sodium hydroxide is, I would say, at least not my solvent of choice. At a certain point, you are quite alkaline for the craft lignins, for instance, which is not so good for your detectors, for your glass windows. If you take it on a long run, it's not 100% clear how stable the lignins are in that sodium hydroxide solution. And when you think about light scattering and aqueous solvents, that is also not the perfect choice. So if you have the choice between an organic solvent and water or an aqueous solvent in light scattering, always go for the more or less organic solvent, because water attracts a lot of dust, and this is usually a problem in light scattering. You cannot use all angles in light scattering, so there are certain restrictions for water. So my preference, if I can, is always an organic solvent. Now, for an organic solvent like THF, and this is a solvent which is on one hand side quite universal. It has a very low UV cutoff. That's why it's used a lot. You don't actually need that low UV cutoff for lignin. A lot of columns are shipped in THF. That's also one reason why people like THF. But THF for lignin is not a very good solvent. You might be able to dissolve an organosolv lignin directly. For the other lignins, you have to do a derivatization reaction. You can, of course, do an acetylation, or you can do a quicker acetopromination. But you have to be aware of the fact that you change your molar mass with that derivatization. And of course, you can say, okay, I can do a phosphorus NMR and measure all my OH groups, my aliphatic ones and my aromatic ones, and then I calculate back. Yeah, it's possible, but it's an extra expensive step. There's also this extra step of doing the acetylation. But if you need it for other reasons, it's a system which works, and I will show you later a quick version where you could nicely measure acetylated lignins. But if you have no other reason to do the acetylation, if you just want to measure a molar mass distribution, maybe you don't opt for this derivatization method. In addition, the whole thing doesn't work for the lignosulfonates because they are very hard to derivatize. So that is something what you have to keep in mind. But once you have acetylated or acetobrominated lignins, you can easily go for a organic solvent like THF. My preference, I have to say, is in organic solvent with a salt. The salt is in a way necessary to prevent aggregation phenomena, which also are in place for lignin. So to have some salt in there, it's usually a good choice. If you use an organic solvent like DMSO, for instance, or DMF or DIMAC, you don't need a derivatization, so you don't change your molar mass. You have to keep in mind that for lignin, you don't have a large number of solvents you can choose from. There's a couple. Quite often people say, yes, but if I have DMSO, I cannot dissolve lignosulfonates. Yes, you can if you protonate them beforehand. They are not soluble if you have them in the ionic form. In that way, they are too much charged. But if you simply protonate them with an anion exchange resin, for instance, you block the charge and then they become soluble. And the same applies for PSS, polystyrene sulfonate standards. So that is something where you have a unique system for lignins, including lignosulfonates. You don't have to derivatize. And usually this DMSO, DMF, including salt, they work also for light scattering. Before I come to the light scattering, I would like to briefly talk about speed. Because the size exclusion chromatography or gel permeation chromatography, also for lignins, takes quite a bit of time. So our classical setup uses 3 columns, and we have a runtime of about 65 minutes for lignin, for instance, here for kraft lignin. If you make a double determination, you end up way above 2 hours. So it's okay if you have 10 samples. If you have 200, it may take a lot of time. So we were looking a little bit for a workaround here. And of course, if you work with a classical gel in your size exclusion columns, you are very limited with the pressure, because otherwise the gel is collapsing at high pressure and you lose your resolution. So in order to increase the pressure and that way also the speed, you need to change your stationary phase. And this is possible since a couple of years, because there are some columns on the market which don't use a gel, but they use a solid state like structure. They're from ethylene bridge hybrid particles. They're extremely stable. They can hold up to 1,200 bars. Just for comparison, in a classical GPC, you have about 50 bars. So it's a lot higher. The whole thing is called advanced polymer chromatography, and it allows you higher speed at a much higher pressure. For a polysaccharide, that would not be a good choice, because at that speed and at that pressure, you may degrade the whole molecule just by shear forces. But for lignin, we are in a range where this could work. So a couple of years ago, we set out and said, okay, let's check it out. Let's see whether that is an option for lignin. And since also these columns are shipped in THF, we first started to work with acetylated lignins. So we had them measured in the application lab in Paris, and we saw, oh yeah, we can basically separate them quite nicely. The resolution is kind of good. And then if you look here, this is 3 columns, and the elution time after that is 9 minutes. So we have a really, really large increase in speed. So it's extremely fast with a very good resolution. But remember, we are still having here acetylated lignins in THF. So we have a gain in speed, we have a gain in resolution, and the molar mass range fits. But if I have to acetylate the sample before I can use that method, I'm using several days for the acetylation in order then to have a speed method. So that makes not a lot of sense. So we said, okay, it would be nice if we could directly measure in a directly dissolving solvent for lignin, and we checked out the DMSO version. The DMSO at high pressure in pure form freezes out in the pump head. It becomes a solid. So the pump stops working at, I don't know exactly how many bars we could reach, but it's not that much. So DMSO alone doesn't work. But anyway, we wanted to use DMSO and lithium bromide. And the lithium bromide here is not just a salt preventing aggregation of our lignin, it also lowers the freezing point. So we depress basically the freezing, and by this certain percentage of lithium bromide, we can go up to about 500-600 bar without the solvent freezing out in the pump head. So it's important that you have the lithium bromide in there, otherwise it doesn't work. And then we can really measure the lignins directly. It's possible for lignosulfonates, and it's possible for lignins as such. Currently, as far as I know, there are 4 different sizes of columns on the market. And depending on the lignin type you want to analyze, you can choose. You don't need to take all 4. So for craft lignin, for instance, we can choose a different set or compared to the lignosulfonates, where we would leave out the very small ones. So, and with that, we get a really huge gain in analysis speed. And we also have a sufficient resolution. And if you look into a direct comparison, so on the right-hand side, same lignin, it's inulin, with the classical GPC, 3 columns, 65 minutes runtime, we get that with 6.5 minutes runtime in the APC. So if you're running out of time, that might be the version to use. So any questions at this point? So I see there's maybe something in the chat. Francisco, nothing, no questions?
Not so far, but maybe we can open. Not so far, but maybe we can open it if someone has a question right now. Does anyone? Doesn't look like.
Okay, perfect. So let's move forward and try to answer the question how we can get absolute for molar mass of lignin. Classical version, Björn has shown it in the last presentation, we take standards. And Björn mentioned we don't have standards for polysaccharides. And the bad news is we don't have standards for lignin either. So same problem. We don't have narrow monodisperse standards for lignin, at least not across the whole molar mass distribution where we need them. So what you see here is the polystyrene sulfonate standard. So these are the black dots here on our classical column. And then we have here a couple of real lignin dimers, trimers, and hexamers. Here you have the structure. And you see they are really off this calibration line. So this is a clear indication that we have a mismatch in hydrodynamic radii. You always have to keep in mind this is a logarithmic scale. So the error we are doing is kind of large. So the polystyrene standards, as are as close as we get in terms of standards which are on the market. But we have to keep in mind that we do a certain, or we have a certain error here. Although there's really no need always to measure absolute. If you always measure against the same set of polystyrene standards and compare samples, it might be perfectly fine. You know, it's always the question, you not always need the absolute numbers, but in basic research, that is a certain interest to go after these absolute numbers. Now, the method of choice is light scattering, which is pretty much established for polymers like cellulose, for instance. And why can't we just apply it also to lignin? And of course, many people tried, and just the basics were explained to you last time. For moles, we don't need standards. We just need one constant. This is the dN by dC, which tells us basically about the polarizability of the molecule. So how well we can polarize it with a, for instance, a laser light. And this dN by dC is important, and this is crucial for molar mass measurements, also for lignin. And you have to keep in mind that the dN by dC, if you take it from literature, changes with the solvent. Of course, it changes with the laser light. So you have to check whether the laser you are using, you have a dN by dC, which is published. Björn already mentioned, if you have a salt system, you need a dN by dC at a chemical equilibrium, mu. So this is also important. So the best version is that you measure it yourself. I don't go into how it's measured, but it's done. It's possible to do it. And then you have basically the so-called SIM equation, which gives you a relationship between your light scattering data, which is the Rayleigh ratio, mainly intensity of your scattered light, and MW. So what comes out of light scattering is really MW, the weight average, or more precise, actually, it should be called the weighted average, because it's a way of weighing the distribution. So we only need the dN by dC. We do a certain error if we have that wrong. It's half so wild in the measurement in combination with SEC. If you have a static measurement, the error would be much larger. Same is true for the influence of the lambda. So we know the dN by dC, we assume that, and we are off and we can measure. That would be true for cellulose. Unfortunately, in lignin, we have a couple of complications. And the major complication is fluorescence and absorption. So those two are a little bit troublesome. And I want to show you why and how. We have to go back to this little scheme here. So the sample is in the middle. We shine a laser light on the sample scatters our light, and this light is collected by the photodiodes, which are arranged in a certain angle around our measuring cell. And what is decisive here is the Rayleigh ratio, so the intensity of our scattered light, which is also a function of the light coming in. Now let's consider the two phenomena. First, fluorescence. So we shine a laser light on our sample, and if the sample shows a fluorescence, it sends out light. And this light is also caught by the photodiodes. So those photodiodes cannot distinguish whether this scattered light is coming from pure scattering phenomena or it's coming from fluorescence. So all of a sudden, those photodiodes catch a lot of light and they think, wow, this molecule is huge. And there are examples in the literature for lignin where you have molar masses of 400,000 upwards. It's not real. It's just a measurement error. And now absorption is also influencing here, because you have here the intensity of the incident radiation. So your laser intensity going in, and depending on where you measure it, if you measure it here and the sample absorbs light, there is less laser light coming here compared to here. So you absorb some of that light, which also influences your Rayleigh ratio just in an opposite direction. So that means in a perfect Mouse measurement, we should not have any fluorescence and not any absorption. So that would be the perfect case. Both not true for lignin. So the example what I have here is nice, because we have separated the lignin on into different fractions. So you see here a sec of those different fractions. The red is the biggest fraction, is done with membranes. So that was left after the biggest membrane. So elutes first, the biggest lignin, and then this is the smallest one. So the olive curve is basically our smallest lignin, which was separated by a 1 kilodalton membrane. So those different lignin fractions have definitely a different molar mass. And we put them into sec moles, and here we have the scattering intensity. So this is basically our mole signal. Bjorn showed it last time. And if you check here, it's funny because all those fractions more or less have the same molecular weight. So they are really the same, but excuse me, they are definitely not the same. We see that from sec. So the scattering intensity here is basically overwritten by fluorescence. So all fractions more or less send out not maybe the same, but quite an amount of fluorescence light, and that overrides basically the information for the scattering, and that's also the information for the molar mass we need. And this has been measured with a laser of 658 nanometer, a red laser, which is quite common in mouse systems nowadays. And that simply means we cannot use mouse. So we get no information on the molecular weight. So now the idea is, what can we do to avoid fluorescence or get away from that phenomenon? And usually what you do is you go to larger wavelengths. You go into the IR region, because the lower your energy, the less fluorescence emission you should have. And then we do that. Before, just one more thing. What is also interesting, I just took out the 10 kilodalton fraction of this different fractions here. And what you also see is it looks like a monodispersed standard. A monodispersed standard would look like this. You have everywhere the same, really the same molecular weight. So if you measure lignin with moles and you get something which looks like this, like a monodispersed standard, this can't be right. Lignin is dispersed. So, and then you can argue, yeah, let's use filters. Yeah, the filters have been used here already, but they are not efficient. Why are they not efficient? What you see here is a filter we just measured with a UV. So we measured the filter directly as a filter for a 488 nanometer laser mole system. And it's a so-called edge filter. So the filter blocks before plus minus 10 nanometers of the wavelengths you are measured. But the wavelengths where you measure, in that case, it's this 488, of course, the filter is open. That means you can apply the filter. It helps you for this region, and it helps you for the region after that. But for the actual laser wavelength region, the filter is open. So in case your lignin sends out fluorescence exactly in that range, you cannot do anything. And this is exactly what we just saw. So also here, we have the filter applied. It doesn't really help us. It's here where it sends out the light. So then let's move, and now we move to the IR mouse. So we have a 785 nanometer mouse. It just came to the market a couple of years ago. It's a bit funny because you don't see the laser anymore. It's in the infrared range, so you have a hard time if you have to adjust the laser. So you can only do that with an infrared camera. And now all of a sudden, we see what we expect. We see the dispersity of lignin. We see that across the molar mass distribution of that fractions, we don't measure the same molecular weight. It goes down as it should go down. We have problems measuring here. This is because these molecules are simply too small. But here we get a nice linear relationship. These are linear columns, so everything is fine. So that was something we expected. Unfortunately, it's still wrong. And this is now not to see that easy anymore. Because what we don't see in this plot is that our lignins also show absorption. How can we see that? Now, that's a bit more complicated, but what we can do basically is we monitor here the forward laser. So we look at what is coming to this forward laser. And this is shown here for a milled wood lignin. You know, the milled wood lignin is mildly isolated. It's slightly yellowish, but it's has a nice color. It's not dark, and basically has no big fluorescence issues. You could even measure it with 660 nanometer. And what we see here is the green is the UV signal, the blue is the RI signal, and here we have the forward laser monitor. So basically this portion here, which monitors the light coming after or is measured after the cell. And we see, okay, milled wood lignin, kind of nice, doesn't absorb any of that laser light. If we look into kraft lignin, we see again RI signal, UV signal, and the forward monitor now shows us a big absorption. So we lose basically light, which is not coming to this point. So we make a mistake here. Fortunately, we have a choice to correct that. And I only know of the wired system, which allows this correction. I don't know of any other systems, but maybe it's possible in other mouse systems as well. Because you have here in this system, so what we see here basically is the measuring cell. This is the laser. This is the beam light basically going into, and in here, so the photodiodes you see here, these are the photodiodes for one side. And we have here this forward laser monitor where we can basically check if we have this absorption. And there's also a laser monitor which is back here, which is basically not affected by this absorption. And we can basically change the reference and use that as a correction. So for the milled wood lignin, we actually don't need that. So we see here two measurements, one with the forward monitor, which is the blue one, and on top, the one with the laser monitor. They are both the same. So there's anyway no need. But if we now go to our kraft lignin, we see here that when we eliminate the absorption phenomena, we come to this blue curve, which is the one without the absorption, which is the one which is more correct. But all of a sudden we see here, oh, wow, this looks not good because we have a residual fluorescence here. Because this is exactly also at 785 nanometers, there is a residual fluorescence also shining, although we still use the filters into our area where our photodiodes are measuring. So we cannot use that for extrapolation. So there is something here, but we can now do a little trick because first we have to correct for this absorption, which kind of counteracts our fluorescence, but we can never be sure if it's exactly the same order of magnitude. So what we do is basically we go to a region, and this is the region where we have in one place a high molar mass. So we have good scattering data. And in this region, the influence of fluorescent compounds is much lower. So there's almost no fluorescence here. And we use that region to extrapolate down to our whole molecular mass distribution and use basically this as a calibration plot. And with that, I would say we get close to absolute numbers. It's never 100% correct, and light scattering never gives you like a 1% for natural polymers like cellulose or lignin, but we are getting pretty close to the actual numbers. What we can do as well is we can now establish some correction factors. People from rice have done that for cellulose many years ago. Berggren, I think, was the author, and it was together with, I think, Elisabeth Sjöholm. You can correct the polystyrene standards and make them more lignin-like, applying the absolute method, light scattering. So you basically assign your polystyrene standards lignin-like numbers and use them for calibration. It's not the perfect choice, but if you can't afford a mouse, that could be something which brings you a little bit more closer to absolute numbers. So that is basically possible. And what we see, maybe just for the lignin as such, that when we apply mouse, we see that the absolute numbers are a little bit larger than what we usually measure for polystyrene. Sometimes it's about double. So if you measure 7,000 for polystyrene, we measure about 14,000. Depends a little bit on the setup for mouse. So lignin is not that small. Maybe one little side topic here, because you talked with Björn a lot about radius of gyration, and to measure the shape in solution. Of course, that would be something super nice for lignin, because we could address cross-linking. We could compare different lignins and measure, okay, how compact is the molecule? Is in the same solvent? Do we see different compact versions? That would be super nice. Unfortunately, our lignin is too small. It's still in the range of the so-called isotropic scatterer. So we have no angular dependency of the scattering of the light, which we observe for large molecules, like for cellulose, for alginates, for different polysaccharides. It's perfect. You can basically really look into the shape of the molecule. In lignin, we are still here in that isotropic scattering range for most cases, and we cannot use that nice feature of mouse unless we have a large lignin molecule. So if you polymerize our lignin molecule, and it's maybe a lignosulfonate, which is as such already much larger, maybe we could get into that region. But so far for lignin, there is no angular dependency of the scattering light. So we don't get anything in terms of radius of gyration and shape. Just to keep in mind, it's a nice idea, but we have to go to X-ray scattering to get information here. For classical light scattering, it's difficult. Okay, and I want to go a little step further now. Maybe questions for the light scattering first.
Yes. Do we have questions from the audience regarding the absolute molecular weight determination with light scattering? I have actually one. I'm curious. You were talking about the DNDC.
Yes.
Which is, yeah, we all know is super important. But I'm thinking now, imagine you have a lignin which has different chemical structure based on size. And then you get, the distribution, and then of course the DNDC might change from slice of elution volume. Is there any way to? It's the same with polysaccharides, but is any way to solve that problem?
Yeah, no. This is like a copolymer or something. So it will change. I would say it will change because of that dispersity we have. So we will make a certain error there for sure. And there's no way to address that, as far as I know, in the software. So we can split the peak into different parts and use a different dN by dC, but then you have to put it together again, which is not so easy to do. On the other side, you can calculate how large your error is, and it depends how strongly your dN by dC changes. And we measured a lot of dN by dCs for different lignins, and it's not extreme, I would say.
Okay, good.
So there's always a discussion. The N by dC is a constant for a polymer, but of course it can be different for the different fractions we have, and it will be different. But there's not a huge change. So the total error is much larger. We do for putting GPC together and all the little problems we have still in light scattering. So I would say still light scattering error 15 to 20%.
Okay.
You have to be super realistic on that topic.
Yeah. Thank you very much. I think you addressed it very nicely. Yes.
But it's a very good question actually. This is something which bothers us also for other polymers.
Yes.
All right.
Yeah,
I want to show you some other methods to separate the different molecules, especially for lignosulfonates. And this is a technique where you actually should have a light scattering or a Mouse for absolute detection, because you cannot rely that nicely on retention times. And what I want to very briefly talk about is this asymmetric field flow fractionation combination with Mouse, which you can use for lignosulfonates. And the nice part here is you can take a black liquor from a lignosulfonate as is. So you can skip the whole purification stage, because you can do the purification right in your molar mass analysis. You probably know lignosulfonates sometimes, especially if you have black liquor, you have all the process chemicals, there's a lot of stuff there. So that is something you definitely would have to take out if you go to a classical SEC column. And that is a tedious process for lignosulfonates, because you cannot simply precipitate that. So you either go through adsorption or ultrafiltration or something. If you apply for your molar mass determination, so-called asymmetric field flow fractionation, you separate your polymeric molecules not on a column, but in a channel. The channel we are using, you see here, it's about 30 centimeters long. It has a certain spacer, and you basically apply your sample within that channel. This channel has a solid top, as you can see here, and on a lower part you have a frit, which is basically permeable, and there is a membrane, and you choose a certain membrane. Of course, you don't want to choose a very large membrane, otherwise you would lose your analyte, in our case our lignin. So we use the smallest possible membrane here, and then we separate the molecule. The way it works is you inject your sample and you focus your sample at the start of this channel, and then you kind of switch on a flow, get a parabolic flow profile, and you have some diffusion phenomena which basically lift the smaller molecules into the middle, which are then taken faster to the detector compared to your large molecules, which are more closely to this membrane here. And you have a separating cross flow here as well. And since this is a permeable membrane, all your process chemicals or your inorganic stuff or your degradation products, so everything which is small, basically is going out through this membrane while you're separating your polymer. So you can basically, at the end, you have to detect, and you get a molar mass distribution as you get for SEC. And what is nice here is that you have no interaction with a stationary phase. So you don't have this troublesome enthalpic interactions you have in a sec. So some inclusion into pores or something like this, it doesn't exist here. And you can apply these dirty samples. The membrane costs about 20 to 50 euros. So you don't have a column set, which costs you 6,000, 7,000 euro. So it's something which is really good for dirty stuff. The only thing what is really more or less needed is that you have a Mal's detection at the end, because your fractogram is not so stable as like an elution from a sec column. So the Mal's is kind of nice here, and you have basically an absolute determination of your molar mass at the end. If you have the right laser, it works quite nicely. This is something which is at the moment only working for lignosulfonates. The graft lignins are too small and the solvents are not ready for that yet. And you discriminate the sample by losing small fractions here, and graft lignin is simply too small. But what is nice, what you see here is this is a lignosulfonate. It's in water, so there are no interaction or water salt. So you have almost a Gaussian distribution. If you ever have seen a lignosulfonate coming out of a sec, looks complicated. And it doesn't look complicated because the lignosulfonate is complicated in its molar mass distribution. It's complicated because you have interaction with the column. So it's artificial, it's artifacts. A lignosulfonate also has a Gaussian distribution. You see that here. Because usually the resolution of fractionation is almost as good as for sec. So that just should ring the bell a little bit in terms of when you do size exclusion chromatography for lignosulfonate in an aqueous solvent. Please be very careful. If the distribution looks super complicated, if you get a lot of peaks, it's not very good resolution. It's interaction with your column material. So again, here we need filters, but basically we get a nice distribution, and that is something if you want, if you're a little lazy, you don't want to isolate your lignosulfonates, or if you have routine with lignosulfonate black liquor isolation, I would say that is a very nice way to do that without purification of the sample. So quick summary, we can do speed sec. It's also possible to couple the speed sec with Mal's, but it's a bit tricky. It's not so straightforward. So I wouldn't say it's at a stage where we have routine analysis for APC with sec. But if this is in place, it would be nice because then it's fast and absolute. We need the IR Mal's for the lignins, especially for the graft lignins. Otherwise, we cannot measure, and we have the possibility to look for corrected standards or to correct standards. So now the question is, okay, this is in place. What can we do now? What is next? What is the next challenge, basically? And we know all that we have a lot of challenges because we still don't understand lignin because of this dispersity. Now, how can we address this? And I just want to cover very quickly at the end a couple ideas here. So we talked already about this dispersity, and of course we can try to address the compositional dispersity. We can measure the functional groups. So far, we do that in an offline mode, but maybe in the future, we find ways to do that online. And we can also look into more general properties like hydrophilicity, hydrophobicity, because that together with the molar mass distribution covers quite a bit of properties we need for applications. So how does a lignosulfonate, for instance, behave in a certain solvent? are there any fractions in this lignosulfonate which maybe counteract my application? Should I take them out? Where are they? And also impurities are important because we are all dealing more or less with technical lignin. If we have to go into applications, we definitely have impurities, and sometimes they're good, sometimes they're really bad. It really depends. Now, if you look into such a offline version, what you see here is basically a craft lignin which has been separated, but separated not via a membrane, but via a prep sec version. And we, of course, know that we have in the small fractions, so this is already the molar mass, we have a lot of extractives, so they usually end up here. In the high molar mass part, we have our silan, but I show you that there's sugar everywhere, also in that lignin. We don't know if it's covalently bound in LCCs or if it's just like strongly adsorbed or adheres to that lignin, but it's there. So, and then we can, of course, measure the different functional groups in here. And in the first place, we did that and came up with some linear relationships. We went a step further. It looks more complicated if you look a little bit closer than that, but we see there is what we call a structural dispersity or functional group dispersity also in lignin. We can look at the different sugar distributions. So basically you see here that or where the hemicelluloses are. So they are mainly in this, but there's a little bit as well here. So that is the sugar distribution. This, of course, changes your aliphatic OH groups when you measure a phosphorus NMR. So it's a good point to have that in mind. And of course, at the moment, we only look for something we know. But of course, there is a lot of stuff we don't look for because we don't know it's there. And this is also something for the future where we probably will find out more and more and more, and basically then look for that structures and look at the distribution of that structures. But if we look at the approach how we analyze lignin, it's usually we take the lignin, we analyze some parameters, or we degrade the lignin and then look into the different structural elements. And then we put this whole picture back again without knowing the template for the jigsaw puzzle. And the whole thing is, of course, in a three-dimensional way. So it's kind of complicated. So let's look out for structures which definitely will influence applications, but we don't even know. And then, of course, just a last thing, development we just started basically is to apply a two-dimensional separation. Of course, you can all the time then also put a mouse detection here. And what we applied was a hydrophobic interaction chromatography, so-called HIC, in the first dimension. And this is followed by size exclusion chromatography in the second dimension. So with that, and this is applied at the moment only to lignosulfonates because of the solubility, with that we can basically separate according to hydrophilicity and to molar mass. And you see here that there are really different distinct fractions in a lignosulfonate which are more or less hydrophilic and have sometimes a totally different molar mass distribution or molar mass. So first we did that offline, and then we switched into an real online 2D mode. It's not so easy because we have a very high salt load in that system. So that is not something which I would call routine at the moment. But you can basically see huge differences between the source of the lignosulfonate, so softwood, hardwood, or the process. Is it magnesium or is it NSSC? So there are quite large differences. At the moment, we call that rather a fingerprint we still need to learn interpretation of that in a way. So how does that link to an application? We don't know yet. So that means we have novel fingerprinting tool, and we want to address this chemical composition heterogeneity in a much faster way than just doing it offline, which is super tedious and you cannot do for many samples, so you don't have samples to compare. And the way to go is to have really automated functionality type distributions. So we call them FTD or dispersity according to functionality. We need this automated sec coupled to whatever, also for craft lignin. That is more difficult. And we are also developing more high-speed methods at the moment, which couple classical chemometry, but with a lot of samples. And this also to some extent for measuring molar mass parameters. That would be then super fast, but at the moment it's super fast, but not super accurate. So with that, I'm at the end. I would like to thank all the co-workers. There are many people involved in that studies over the years. And I would like to thank